Week 15, here we go. So we are covering lessons 115, 116, and 117, and 118. So most of the weeks this semester we've only done 2 or 3. This one, just because of the way it times out, we have to do 4. But the good news is we're getting through 118. That means we have 119, 120, and that's it for new lessons in the book. So we are nearing the end, which is really exciting for you guys. You've done great so far this year. So let's finish strong. All right, so lesson 115, we can flip over there. Make sure I'm showing. Okay. So writing percents as fractions, part 2. Okay, part 2 meaning we've really done percents, fractions, and decimals, and worked out to change them back and forth all year. And so we're just looking at more of that. So again, something simple like 50%. Well, 50% means per 100, so 50 over 100. 50 goes into both of them. We could reduce it down to 1/2. Okay. Some aren't going to be as easy, like 33 and a third. Percent means per 100. Well, this is a complex fraction, so we can do this, but what we need to do is we need to first convert this to an improper fraction. Dividend, so we do 33 times 3 plus 1, so 33 times 3 is 99 plus 1 is 100. So this top portion we can rewrite as 100 over 3. And then dividing by 100 is the same as multiplying by 1 over 100. Just like dividing by 2 and multiplying by 1/2 is the same thing. So when we break it apart like this, it just makes it visually a little bit easier, because then we see, 100 and 100 would cancel out. We could do the multiplication and then simplify, or we can reduce before we even have to multiply. So let's factor out to just be 1. So we're left with 1 times 1 over 3 times 1, so 1/3. So 33 and a third percent means per 100, and we're dividing by fractions, so we gotta make it an improper fraction. Dividing by 100, that's the same as multiplying by the reciprocal, which is 1 over 100, and then all of that to give us 1/3. That's what we come up with. So now let's say we have 3 and a third. 3 and a third percent, so per 100, so now we're going to multiply by 1 over 100, because dividing by 100, with fractions, it's multiplying by the reciprocal, keep, change, flip. Let's start back here. So first, we know this is a percent, so let's first make it an improper fraction. 3 times 3 is 9, plus 1 is 10 thirds, and we're going to multiply it by 1 over 100. 10 goes into both of them. 10 goes into 100 10 times, and 10 1 times, and left with 1 times 1 over 3 times 10. So just like 33 and a third was 1/3, well, 3 and 1/3 becomes 1/30th. Okay, so that's our only example. We will go over these together. We'll play around. There may be a way, I think we can do this in our calculator. If we do the fraction and then divide by 100, that will give us a decimal, and then we'll have to convert it back to a fraction. So for a lot of them, it may be easier to just do this method by hand, but I'm sure there's a way we could use the calculator to verify what we found doing that. We'll go over that practice set together in class. So lesson 116, we're looking at compound interest. Again, maybe you've heard of interest rates. Interest rates, they're always on headlines. You always hear people that work in sales or own homes, or people that are saving and investing. They talk about interest rates. So an interest rate, to attract deposit, bank offers to pay interest percentage of money deposited. So interest rate when it's our money, whether we're putting it into an investment, or we're putting it into a bank or a savings account or checking or CD or whatever it is, type of account, we want higher interest is better. it's our money, higher interest means it's going to grow faster. When it's money we're paying back, we want lower interest because we don't want to pay back um, any more than we have to. So if we're taking out a loan and they have the same loan uh, amount, and one's offered at 3%, one's offered at 6%, well, it's a loan, we're going to pay it back, so we want 3% instead of 6%, just for an example. So that's interest. Principal, the amount deposited, so the money we start with, that's called the principal. Simple interest means it's going up at the same rate every year. So it's linear, so to speak. It's just going to go up by 3% of the principal. Compound interest is better for us in the long run, as we'll see right here, but it's a little bit more complicated, but it's definitely better because our money is going to grow at a faster rate. So it's going to accelerate over time. It's going to grow exponentially instead of just linearly. Simple interest. So 3%, principal is $100. So that's what we start with. That's what we put into our bank account. It tells us we get 3% interest, simple interest every year. So 3% of 100 is $3. So we make that $3 year one, $3 year two, $3 year three. So after 3 years, we've made $9 on a $100 principal investment. So simple interest is probably better for an account where you're going to be putting money in and out. You're not really expecting it to grow over time, because even if you let it sit there for 40 years, you've made $120. But 40 years, you've made $120. Not probably going to retire on that. So that's simple interest. It's just going up by the same amount each year. Compound interest, it's going up by 3%, but then the new starting point is the new amount. So if we look at this, so we go up by $3 the first year, so nothing different there. But instead of year two, it's 3% of 100. It's now 3% of $103. And then year three, we're taking year two as our starting point and getting 3% of that. So you say, oh, well, big whoop. After 3 years, we have 27 extra cents. Yes, I agree. If we're only at 3% and only investing $100 and keeping it in there for 3 years, it's not that big of a difference. But let's say I'm just trying to do. So I was just trying to maybe jump a little bit ahead because use exponents in this. But let's say we have, well, let's just graph it to make it a little bit easier. Let's say we have $100,000 and we're multiplying it by 3, so 3%. Let's just do 10,000. So we graph it. Zoom. Okay. We'll look at an example in class. I calculated the window's too big, but you can really start to see the benefit of compound interest when we're looking at bigger amounts. So let's start here. Miss Vasquez opened $2,000 retirement account that's grown 10% a year for 3 years. So if you ever see anything double digits, 10%, jump on it. That's great. People are usually excited if they get 7, 8%, whether it's appreciation in their house or an account that they have, or an investment that they have, something like that. So 10% would be really good. I'd be putting more than $2,000 into it. So in looking at 2,000, 10% of that is $200. So 2,200. Now, for the next year, there were $2,200. We're doing 10%. This is compound interest. So we're getting 10% of 2,200, not 2,000. That's an important difference. So we get $220. So it's 2,420. That's our new starting point. So 10%. So 2,662. Whereas if we would have just went up by the 200 each time, we'd be at 2,600. So yeah, after 3 years, $62 at $2,000. But imagine this was $2 million, and we did this for 30 years. You can see how quick it's going to grow over time. So we're going to do. Okay, so this is showing what we could do in our calculator. So that's, I'm going to show you the graph. If we can at least show you how to calculate it. So we had $2,000 that we started with. So 100% of that, 100% as a number is just 1. So we multiply it times 1. And that 10%, we would, 10% would be 110%. So 1.1 would be the value. So after year 1, then we can do it by the second year. 30. Oops, sorry. So there's our third year. We can also do it this way. We can say 2,000 times 1.1 to the power of whatever year we're looking at. Let's say what would it look like after 20 years? We could go through and do this year 1, 2, 3, 4, 5, 6, all the way 20 times. Or we know it's 1.1 to the power of whatever year we have. So after 20 years, oh wow, that's really good. Her $2,000, it's a retirement account, so she's probably not planning on just sitting in there for 6 months or a year or even 5 years. She probably wants it in there for a long time. At this 10% rate, compounding annually, she's now at $13,452. So her $2,000 over 20 years is now worth that amount. So you can see how much quicker it can grow. Whereas if 2,000 to 10%, so it would have gone up by. So that if it was just simple interest, she started at 2,000 and 200. She's going up by 200 every year if it's just the simple interest. So what do you say after 20 years? So $6,000. But we look back at the difference. Okay, compound. Okay, so 10% of 2,000 is 200. So times the 20 years, we get 200 every year. So by 20 years, it's 6,000. Whereas this is what I was trying to show the difference between. I was trying to graph it, but this works too. If we do the compounding interest, it's going up exponentially. So you can see the difference, just the difference between simple and compound interest. Same rate, same principal, same starting balance, everything. This one's over 13,000, whereas this one is 6,000. So obviously, if we were given the choice, we're going to let a. And again, like I said, $2,000 to you guys may seem like a lot of money, but for grown-ups who are looking at retirement, that's not very much money whatsoever. So just at $2,000, we see kind of that exaggerated difference. Now, if you think, what about $200,000, or like I said, $900,000 or $1.5 million, it really will be a huge disparity between those numbers. All right, we'll go over those practice set examples together. 117, finding a whole when a fraction is known. Okay, so 2/5 of the students in the class are boys. If there are 10 boys in the class, how many students are in the class? So fifths tells us that there's 1, 2, 3, 4, 5 groups. 2 of the fifths were boys, which means 3 of the fifths are girls. If there are 10 boys in the class, how many students are there? Okay, so we know that there's going to be 10 divided by 2 groups. Okay, so 2/5. So 2 of the groups two of these sections are 10 boys, so 5 and 5 is where we get 10. So we know each one of these has to have 5 in them, so there's 25 students in the class. So a couple different ways we can solve these types of problems. Let's look at example 1. 3/8 of the townspeople voted. If 120 of the townspeople voted, how many people live in the town? So let's go over. So the method they use, I'm not saying this is wrong, I just want to. Let me see, it's a little bit more time consuming. I think if you're a visual learner, this method may be really beneficial to you. If you just like equations and numbers and put it directly in, I'll show you two different ways to solve this. So we're told 3/8 voted. So that's why I have 1, 2, 3, 4, 5, 6, 7, 8 sections. We were told 3/8 voted. 3/8 voted. We know without even being told that means 5/8 did not vote. If 120 of the townspeople voted, so 120 voted, so that 120 needs to be divided into these three. That means there's 40 adults or registered voters or townspeople, whatever you want to call them, in this. That means there's 40 in all of these. And so we have 8 equal groups of 40 people in there. And we're asked to find how many people live in the town. We're going to do 40 plus 40 plus 40, or 40 times 8, which is, 4 times 8 is 32, so 40 times 8 is 320. Nothing wrong with that, drawn out. It's just, let's say we had 50 groups or something, or we said 13/50ths or something. We won't see anything like that today, but if we had that, we would need to do 50 groups. That's going to take a long time. 8 isn't terrible, but that's why I think there's an easier way to do this. So I would show you how I would go about solving this. So 3/8 of the townspeople is 120. So 3/8 of the people voted, there was 120. So 3/8 of a number equals 120. We divide by a fraction that's the same as multiplying by the reciprocal. So 8/3 times 3/8 comes out to be 24/24, which is just 1. So, or we can just cancel out the 4. Multiplied by 8/3 over here, I got to do the same thing over here. So 3 goes into 3 once. Into 120 40 times, so I'm left with 40 times 8, which is 320. So this way, to me, is a lot easier. It's quicker. I don't have to draw up all the sections. But the other method, if that works for you, by all means, do it. I just want to show you there's both ways to do it. And we've done this. 1/2 of what number equals 40 or whatever. We've seen some word problems like this. So I would set it up directly into an equation, inverse operations to solve for my unknown. If the other method works for you, then nothing wrong with that either. 6 is 2/3 of what number? 6 is equals 2/3 of what number? Again, I know there's 3 groups. 2/3 is 6, so we know it's going to be split into 3 and 3. This would also have to be 3, so we know 3 plus 3 plus 3 is 9. Okay. Also, we can go back here and dividing by a fraction and multiplying by the reciprocal. Simplifying, we end up with either 18 over 2, which is 9, or reduced before we multiply, we get 3 times 3, which is 9. Either way, we come up with the same answer. So if it says to do a certain method, it says to use this method, and you don't, and you use this method and still get the right answer, I'm okay with that. You'll start to find certain ways that you prefer to solve problems, and there's nothing wrong with that. All right, our last one we're going to look at is estimating area. So if we look in here, so again, we know this is circular, so we count the radius, pi, radius of 3 squared. But again, let's say it's a lake or something and it's not equal. Again, okay, so let's look at what they're doing. I think we did this, yeah, lesson 86. We counted our full or mostly full, and then our partials, and we added them up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and then 25, 26, 27, 28. Okay, if we count these as halves. But again, that's not exact. So if it's perfectly circular, we know how to find the area of a circle. But when this can maybe applicable is when we have like a lake or something. This is an aerial photograph of a lake. We have an overlay. It's in acres. So in this, we would go through and count up. It looks like we have what they did for us. So partial or mostly partials, you're going to want to call a whole, and then we're going to do these little dots for our partials. Okay. So 1, 2, 3, 4, 5, 6, all the way to 37, and then we have these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 partials. So 37 plus 5 or 6 would get us to about 42 acres. So again, if it's a perfect polygon or perfectly circular or something, probably don't need to use this grid counting method. But if it is something like this, like in nature, we're seeing a lake that's perfectly circular or anything, it's always got a shoreline that has all these different in cuts and outs, and it's never perfectly straight lines anywhere. So in order to calculate that, we probably need to use this to come up with how many acres. And then volume, we'd obviously need to calculate depths and things like that. Okay, practice set's pretty easy. It's just this one. That is all for 118, and that's all for this week. So we will see you guys in class. Thank you.